In this video, we're continuing this derivation of looking at the relativistic effects of, say, magnetism. And so what we have is here, so the problem we started with was we have two lines of charge, a negative charge moving to the left, a positive line of charge moving to the right. They each have a charge density of lambda, um, and in their rest frame, they measure their certain charge density. In a frame S, since they're moving with a velocity, then they have a contracted line density. In a frame S bar, right here, where the frame itself is moving with the velocity u with respect to the line densities, the net charge is given right here. So that is the net charge measured in frame S bar, which is moving with a velocity u, and there's a point charge which is also moving with the velocity u. So from the frame S bar's perspective, the point charge q is not moving, but the line charges have now been length contracted, and therefore we get this net charge building up. From Gauss's law, the electric field measured in the frame S bar is the net charge densities over 2 pi epsilon naught, the distance S, so that's this distance right here, of the point charge from the line charges. And again, remember, this is in frame S bar. Okay. That means the force in the bar system is the charge times the electric field, which in this case would be minus lambda V. So if we put in the equation for lambda net, so lambda V pi epsilon naught c squared s q u over 1 minus u over c quantity squared. Okay, so that would be the force that the person in frame S bar would see. Okay, in the frame S now, what force would they see? Well, we can do a Lorentz transformation, and this force F would be 1 over gamma, so 1 minus u over c quantity squared times F bar, which would then give you minus lambda v over pi epsilon naught c squared q u over the distance s. Okay. Now, if you remember that the speed of light, c squared, is 1 over mu naught epsilon naught, and the current is 2 times the charge density times the velocity, then lambda v is current over 2, and if we plug this in, we would get minus qu, the current, over 2 pi epsilon naught 1 over epsilon naught mu naught s, which gives us minus qu mu naught, the current, divided by 2 pi over s. And so if you remember from earlier chapters, this looks like a magnetic field of a line of charge, or a current. So that's the magnetic field of a current going through a wire. So the conclusion then is that what started out as a derivation of an electric field in one frame, so in frame S bar, the interaction looks like it's an electric field, while in frame S, the interaction now appears to be a B field. And so that's what's going to save us with special relativity in terms of fields, is that the electric field and the magnetic field are going to turn out to be basically one and the same object. The behavior of an electric field in one frame is going to turn out to be the behavior of a magnetic field in another frame. So we can look at now, what we want to do is move beyond just doing examples and come up with a general formula for this. And so what we can do is take a look at one more example of how this is going to modify things. And let's take a look at something like now parallel plates. So let's say we have two parallel plates. Like so, or on the top plate, you have the negative charge. On the bottom plate, you have the positive charge. This is the y direction. This is the x direction. This is the z direction. And actually, let me switch those around. So let's make this x, and I'll make this z. And now I'm going to be labeling them as with zeros instead of bars. The width of the plate is w. The height of the plate is y. And the length of the plate is L. And I'm going to call this L0. And now, let's say this is in a frame of reference that is at rest. If we now look at this in a frame that is moving, so let's say now we move the whole system. Like so, where this is still the length width, this is still the width of W, this still has a height of Y, but now, since the frame is now moving with a velocity v0 relative to the one at rest, the length of it now is L. So you can kind of think of this as this is frame S, and this is frame S bar, where S bar is now moving with respect to S. Where S claims they're at rest, and S now sees that frame S is moving with respect to itself. So in frame S, the electric field would be sigma 0 epsilon naught in the y direction. In frame S bar, it would be sigma over epsilon naught in the y direction. Now the charges are not the same because these are charge densities. And so what happens is W and Y are perpendicular to V, so they don't change. However, L naught is parallel to V, so it does change, and what you get is a contraction of that length. Since there is a contraction of the length, then therefore the charge density is going to be modified by the relativistic factor gamma, and I'm only putting the 0 in because it's related to the velocity 0, times the original rest frame charge density. So what is this gamma? So this gamma is the usual 1 over square root 1 minus V0 over C quantity squared. Okay, so therefore there will be a difference in a measured electric field in each frame because there's been a contraction of the length of the plates. The plates are not measured to be the same in each frame of reference. Okay, so in the next, what we're going to go forward with is we're going to now do this in a general case. We'll start with Coulomb's law, and then we will generalize the contractions that you would see in the electric field, and then we will apply those in two different frames that are moving relative to each other with a velocity, and then we'll hope to generalize the appearance of the fields in each frame.